As was just mentioned, my name is Chris Eliasmith, and I'm the CEO of Applied Brain Research, or ABR. ABR is building chips to help device makers wow their customers with cool new features. Things like on-device spoken user manuals, or hyper-accurate heartbeat monitoring, or in-ear real-time translation. So let me dive into that first one a little bit just to paint a picture. Imagine that you buy a complicated consumer device of some kind. Suppose it's a camera. So there's tons of features on these devices. They're very complicated. And typically, to come to know how to use them, you can read the manual. No one reads the manual. Or you can try to make your way through all of the menus that some engineer has designed, which might be overly complicated. Either way, this is not a great user experience. Discoverability is a real problem. Imagine if instead you could just talk to the device. You could say, how do I turn off the autofocus? How do I take an HDR photo? And it would just tell you how. This is a much improved user experience. Discoverability is no longer a problem. Or imagine instead you have a tiny little device. You don't need a phone. You don't need the internet. You pop it into your ear, and now you can understand foreign languages that are being spoken around you. That's almost sci-fi. Right now, hardware is not out there that allows this to happen. If you look at extreme edge hardware, you find devices under 100 milliwatts that can do things like keyword spotting, key phrase detection, and simple event detection. But of course, that's not going to improve the user experience in the case of the camera. You have to now remember a bunch of keywords or a bunch of key phrases. ABR is introducing technology that we call the time series processor. We're introducing two products. One we call the chat chip, and the other signal chip. Chat chip is focused on speech technology. So for less than 50 milliwatts, we can do full speech recognition, real-time streaming. We can do language modeling, translation, which is what you need language models for, text-to-speech, and many others. On the signal side, in the same kind of power envelope, less than 50 milliwatts, we can do advanced biosignal processing. So right now, we actually have a customer who is licensing our technology in order to do heartbeat detection in a fairly difficult case where you've got a dry sensor that's sitting on the skin and people can move around. So this means that you have all kinds of noise artifacts as well as just complete signal dropout. And our technology is able to handle that. We significantly increase their accuracy for doing heartbeat detection and massively reduce the number of resources that were required. And you can also do things like anomaly detection. So in the case of heartbeats, AFib. In short, ABR is enabling previously unachievable edge applications. So how are we doing this? I think unlike maybe any other AI hardware company, we actually started with the algorithm. So we invented a brand new algorithm. This is called the Legendre memory unit. It's got some really nice mathematical properties. You can actually prove it's optimal for these time series cases, which is very unusual for neural networks, if you're familiar with them. Large companies like DeepMind are now citing our work and saying this is a new class of algorithm, which has very significant advantages, especially in doing time series processing. So unsurprisingly, we've run this on a whole slew of benchmarks. We've shown state of the art on many of them. We get typically improvements both in accuracy and a reduction in the amount of resources required. And we've also built a full stack. So you can right now go and upload your data, pick a piece of hardware, an M4, M7, or TPU, pick an LMU architecture you'd like to train, and then just hit go. And it does quantization-aware training, make sure that everything fits on the chip, and we'll actually run that on that piece of hardware in the cloud so you can get real-world metrics, things like latency, accuracy, power, and so on. And of course, we're going to put our own piece of hardware under the same stack. And the hardware itself isn't super complicated. It's a lot of MRAM, which we picked for the memory density. And then, of course, LMU logic. So that's to run that particular algorithm really efficiently. And we know exactly how the data is flowing through the chip. So we can turn off all the parts of the chip that aren't being used. And this is why we can get what's often considered large AI to be running less than 50 milliwatts. We're taping the chip out in November of this year. And a few months later, we're going to release our dev kit so our customers can start seeing the results of the LMU running right on the hardware. I think one way to understand the sort of niche that this piece of hardware falls into is shown by this graph. So if you look at full ASR-capable chips currently on the market, you see that they're typically running up in the 10-watt kind of regime. We're less than 50 milliwatts, so over 100x improvement in power. And because the chip is much smaller, of course, we also have about a 10x reduction in price. It's also interesting if you go look at ML Commons. So this is where it's a hardware consortium. They've collected a whole bunch of benchmarks for different hardware companies to compare. If you look at what they've got, you'll notice that there's really no benchmark that kind of covers this power and capability. If you look at this sort of power regime, you find things like keyword spotting and all the stuff I mentioned before. And if you find things like language modeling and full speech recognition, then you're typically up in the tens of watts. From a customer traction perspective, I already mentioned our one wearable customer. We also have another customer in speech technology. It's actually another medical application in the operating room. And we're in conversation with several other customers. But really our focus right now is on the MPW, making sure that we get that out in November. And as I mentioned, releasing the dev kit. One thing that's actually turned out to be quite an advantage, starting with the algorithm, is we can work with customers now using the hardware that they already have and show the advantages that the algorithm alone gives them. And once they've seen those, of course, they're kind of sold. This gets a foot in the door, and then we can say, would you like to now reduce your power by 10 to 100x, then buy the hardware. And this has already worked with our wearable customer. We have lots of experience working with a wide variety of customers, so we actually are able to not only provide hardware, dev kits, and so on, but we can provide full turnkey solution. You can see some examples of our customers here. From a financial perspective, we're expecting to break even about 2 years after we release our dev kit, and our first production chips should be out next year. We've managed to find a couple of sources of non-dilutive funding from the Canadian government. We're expecting that money to start flowing in the fall. And I should also mention that we're about to kick off a seed round. If that's something of interest, please track me down. Last but not least, as Tarun mentioned, this is our first opportunity to talk to Silicon Catalyst. We had a great day yesterday and looking forward to more conversations today. As you can see, we've been set up with a really impressive group of advisors, many of whom are sitting in the room here. And I think it's fair to say that as a group, we're super excited to be bringing a technology to market, which is just going to shatter people's expectations about how much intelligence you can get on a device without it being connected at all to the internet. Thanks, I'm happy to take questions.
Thank you, Chris.